Welcome to AI with Justin. In this video, I'm going to be covering the main components of state-of-the-art large language models, or LLMs. These are the sections I've divided the video into. There are timestamps in the description. LLMs are typically first pre-trained on a large and general dataset using an unsupervised objective, then later fine-tuned in some way or form for the given task, purpose, or domain they will be applied to. Seeing that pre-training corpora is generally the initial prior to the model, it's a natural topic to begin this video with. Although multimodality is beginning to gain some of the spotlight, large models specifically restricted to the space of text, thus LLMs, have been the priority of researchers thus far. Just as the models themselves are large and rapidly growing, so are the datasets. These charts show a selection of well-known LLMs and their corresponding pre-training corpus size. Note that the chart on the left has a linear y-axis, and the chart on the right has a logarithmic y-axis. LLMs in 2021, such as Megatron Turing NLG and Gopher, were trained on corpora of size greater than a terabyte. So where do datasets of such size come from? Well, given that the goal of LLM pre-training is to produce a generalized representation of language, and language is ideally a representation of the world, researchers have been selecting corpora from a diverse, widely ranging sources which are trusted to be high quality, in quotes. What high quality means is up to the researchers, but generally implies composed of factual, accurate, and logical statements, diverse in gender, racial, or cultural biases, anonymous of personal information, comprehensive in subject, and whatever other characteristics the researchers desire to instill in the model. The information provided to the model directly shapes what it will become. I'll speak more about this concept in the training section of the video. Next, I'm going to give more specific examples of what data is included in these corpora and how they've progressed over time. GPT-1 and BERT kicked off the LLM boom in the second half of 2018, each trained on a collection of unpublished books, and BERT also on Wikipedia. In 2019, Roberta and GPT-2 corpora included news articles and some public websites, especially Reddit. Sites were filtered heuristically for quality, such as by number of upvotes. In late 2019, the number of individual sites researchers sourced from grew dramatically as massive general web scrape data sites were created and/or became popular. These sources included wide varieties of academic sites like scientific journals, code repositories, educational sites, and many more. Companies with access to social media conversations also began to leverage their dialogue and conversational data. Fast forward to 2021, and while corpora is often larger than a whole terabyte and better quality data is always desired, pre-training dataset size has yet to be a central limiting factor. LLMs to date are always trained for a single epoch and show worse performance when trained for multiple epochs, even when trained with significantly greater total compute. Alright, so once pre-training corpora is defined and ready, that data needs to be prepared and converted into a format in which the model can both process it as well as best learn to represent it. Step 1 to do so is cleaning, things like removing duplication, removing website HTML tags or other structural non-content text, removing unexpected characters, and much more. After cleaning, sometimes stop word removal, lemmatization, and word embedding conversion is done. Stop words are words that might have little or no significance in a sentence, such as a, and, the, etc. Lemmatization is a reduction of words to their base form, such as reducing running to run. Word embedding conversion is converting each word to the embedding supplied by another model or algorithm. While these three techniques are historically popular in NLP, they seem to be being phased out. The most recent models use very little or no amounts of these techniques. Lastly, the text is encoded into tokens, which will be fed into the model. These tokens are typically not individual characters, and neither are they individual words, but rather somewhere in between the two. Why? Well, tokens composed of individual characters lack much of the information or inherent meaning which can be derived by sequential characters in a word or parts of words. While the model can learn these meanings implicitly, tokenization can be performed in a way which explicitly assists the model in this task. Further deterring character-level tokenization is the fact that the smaller the tokens are, the more total tokens are provided as input, and thus the larger the computation costs. So that's why character-level tokenization isn't ideal. What about word-level tokenization? Of course, feeding the model the entire word will also provide context beyond individual characters. However, the model requires a fixed vocabulary size. When the model outputs a token, it's selecting from a vocabulary. The broader this vocabulary is, the larger the selection challenge may become. Any modern language is likely to have hundreds of thousands of words. Further, it's not just about technical limitations. Splitting a word into subsets can often make the meaning of the word more apparent via the structure of the language itself. For example, in the word psychology, psych refers to mind, mental, and psyche, and ology refers to the study of. One of the most popular encoding algorithms is named byte pair encoding, or BPE. BPE is a greedy algorithm which, in most variations, intakes a target vocab size, then iteratively merges the most frequently occurring pairs of characters in the corpus until the target vocab size is met. Let's walk through an example of how it works. Given the corpus apple, banana, cranberry, and apricot, the corresponding vocab and frequencies will be as follows. On iteration 1, we look through our corpus and see that AN occurs 3 times and is the most frequently occurring pair, so we merge them. And our vocab is updated. Now, on iteration 2, we observe that AP occurs twice and is now the most frequently occurring pair, so they get merged. And our new vocab will be. Alternative stopping conditions to meeting vocab size can be used for BPE, and in this toy example, I'll stop because there are no further pairs with greater than 1 frequency. BPE has many variations which are used to better construct the encoding for purposes like multi-language vocabularies or various text types and text characteristics. For example, models representing more languages will naturally have more tokens in their vocabulary. Alright, we've covered how data is prepared for the model. Let's start talking about the model architecture itself. Gated recurrent networks, such as LSTMs and GRUs, dominated as the central architecture in NLP for numerous years prior to the invention of the transformer. Elmo, a bidirectional LSTM network released in 2018, even demonstrated that the trend of scaling parameters pre-existed the popularity of transformers. However, the rapid growth in size and capabilities of modern LLMs would not be achieved with gated RNNs, seeing that they had a few major limitations. I'll list what I think are the most important 3. 1. They have difficulty with long-term dependencies, as each iteration degrades gradients, even with gating. 2. They cannot be parallelized well, which would deter scaling to the extent which is present in transformer-based models today. 3. They don't inherently focus relevant sections of the input sequence. Transformer-based models do not experience these drawbacks to the same degree, and have been the central architecture of LLMs essentially since they were invented in mid-2017. I'll briefly summarize on a surface level how and why they work, but for a more in-depth study, I've linked some of my favorite transformer-specific resources in the description. I'm going to explain the transformer from a top-down perspective. The original transformer design has two main outer components, encoders and decoders. There are multiple blocks or sections within each. In this diagram, I show 3 blocks for each, but the number of blocks is variable, oftentimes it's 6. The first encoder block receives the input tokens with positional information encoded. Positional information is injected using a sinusoidal function, where essentially the output from this function is added to the input vector, and the model then learns on its own to recognize or utilize the additions to better understand order and sequencing information. All following encoder blocks receive the previous encoder block's output. The first decoder block receives the input tokens and any previously output tokens, both with positional information encoded, as well as the output from the final encoder block. All following decoder blocks receive the output from the previous decoder block, as well as the input from the final encoder block. Importantly, during training, tokens which the decoder has not yet predicted are masked. On a side, note that it has been common for models to adapt an encoder or decoder only transformer structure. Studies from T5 in 2020 suggest that encoder-decoder models may be the most effective use of parameters overall, but given implementation and parallelization challenges, utilizing encoder or decoder only architecture has been most popular thus far. The majority of the most impressive models so far have been decoder only. Moving to the block level now. There are 4 main components among encoder and decoder blocks: feed-forward layers, self-attention, encoder-decoder intention, and layer normalization. The layer normalization mechanism applies normalization across the feature dimension, differently from the commonly used batch normalization. This is ideal for language modeling because if inference is not done in batches, which is uncommon in most NLP applications, then you can't normalize via batch. Note that I'm going to exclude it from upcoming diagrams for simplicity. Let's take a look at an encoder block. An encoder block has a self-attention component and a feed-forward component. The feed-forward component is typically densely connected and is the largest learnable part of the architecture. Attention blocks are also learnable, but typically just with one linear layer, and are the core feature of transformers. So what is attention anyways? Attention is a mechanism that calculates a score between each element in 2 sequences. This score can be thought of as perhaps the importance or relevance between the elements. In short, it does this by transforming the input sequence into query, key, and value vectors, performing a similarity calculation between the query and key vectors, and returning the scaled and normalized value vector result. Notably, the transformation from input vector to each QKV vector is a separate, linear, and learnable projection. Also important is that each QKV vector is split n ways and passed through the similarity calculation independently. This split makes attention multi-headed and allows more than one score to be calculated between individual element relations, theoretically allowing the model to learn multi-dimensional relationships within each element comparison. So in practice, it's not whole tokens relating to each other, as in the example on the screen, but rather certain dimensions of each token. Attention is a complicated subject. As I mentioned earlier, there are recommended resources in the description to dive into this topic further. If you're new to attention, just understand that in essence, it greatly enhances the model's ability to selectively focus relationships between different parts of the input. Now let's take a look at the decoder block. which has self-attention and feed-forward layers, just like the encoder, as well as encoder-decoder attention. Self-attention and encoder-decoder attention differ only in the sources of input provided to them. Self-attention applies attention from the input sequence to itself, whereas encoder-decoder attention applies attention from the encoder output to the decoder input. To be more specific, in a self-attention, all vectors are sourced from the vector provided by the prior block. In encoder-decoder attention, the Q vector is sourced from the prior decoder block, but the key and value vectors are sourced from the encoder block's output. While the transformer architecture is the key ingredient in modern LLMs, it is scale which enables the complex behavior we've observed. Between 2018 and 2023, model parameter count increased at a nearly exponential rate. Note that the figure on the left displays a linear y-axis, and the figure on the right displays a logarithmic y-axis. The training phases for these recent models extends over multiple months and costs many millions of dollars, even with large advances in training efficiency and parallelism. Research openness has begun to narrow over this time period for multiple reasons, in particular rapidly growing business competition pressures. So, while less precise information is known about the architectural and training details in 2022 and 23, multiple sources have indicated or hinted that this exponential growth in parameter count is slowing. Some sources claim available computation is meeting an upper bound, which may literally be the number of processors that can be built. Others cite that many current LLMs are underfit, and that resources are being allocated to training on more total tokens. DeepMind supported this, providing a compute equivalent study in which a smaller model trained on more tokens outperformed a significantly larger model trained on fewer tokens. More sources claim that research companies are focusing on building new components, such as multimodality, logical behavior instruction, external retrieval, and more. I'll return to these topics in the last section of this video. So, given massive transformer-based architectures, what training strategies are used to configure its parameters? Training for LLMs is commonly multi-stage and begins with general pre-training on a multi-domain corpus using an unsupervised objective. There have been two main families of unsupervised objectives thus far. The first is next token prediction, often just called somewhat ambiguously language modeling, where the model is tasked to predict the next token in the given sequence. Notably, this is the pre-training objective of OpenAI's GPT series. Next token prediction is autoregressive, meaning the model can use its own outputs to create further outputs. The second is fill-in-the-blank prediction, also called masked language modeling, or a denoising objective, or an autoencoding objective, in which one or some tokens within the given sequence are masked, and the model learns to predict them. This approach was popularized by Google's BERT. Notably, this masked language modeling is not naturally autoregressive. It is, however, bidirectional, or perhaps more accurately, non-directional. What is meant by this is that the predictions the model makes take into account context from either direction in the given sequence. Next token prediction only uses context preceding the target token, which is potentially a limiting factor given that the meaning of a word in most languages is naturally dependent on the context from the entire sequence. Multiple studies have provided support indicating that fill-in-the-blank objectives are actually more effective per token, however, not by an amount significant enough to deter the field from gravitating towards next token prediction, again favoring implementation and parallelization ease over marginal gains, which makes sense when reminded that the computational budget has been the bottleneck, not availability of tokens. Notably, there are many variations of both of these objectives, One shown to be especially effective and growing in popularity is to predict spans of tokens rather than just individual ones. So what exactly is the model learning during this pre-training stage anyways? Well, whatever it takes to accurately predict the next token. This might be language-specific statistical patterns or regularities. It might be how to relate contextual information. It's certainly world facts and associations and other concepts. The openness of this task allows for a very complex and obscure representation. The next clip is of Ilya Sutskever, chief scientist at OpenAI.
Look, if you think about it, what does it mean to predict the next token well enough? What does it mean actually? It's a deeper question than it seems. Predicting the next token well means that you understand the underlying reality that led to the creation of that token.
Okay, moving on to fine-tuning. In 2018, following the pre-training stage, multiple copies of the pre-trained model would typically then be fine-tuned in a supervised fashion separately for individual test sets or applications. This is still common in some applications and research areas. However, the potential to apply these models as generalist rather than specialist has gained the focus of large research groups and companies. As a result, non-task specific strategies for refining the models have become popular. One of these strategies involves no modification of the model's weights, but rather purposeful construction of the model's input. As models grew and overall performance rose, models became successful in 0, 1, and few shot settings. A 0 shot setting is one in which the model is pre-trained, but no fine-tuning is actually performed. 1 and few shot settings are when a model is supplied either a single example or a few examples of the desired task in its prompt. No fine-tuning changes are actually made to the weights. This idea of organizing the model's prompt to target its output has been shown to be extremely valuable. It has been shown to increase the model's performance on domain-specific tasks by large amounts, both without requiring a fine-tuning dataset or the computational resources to perform the fine-tuning. This has been extremely valuable to end users building application-specific use cases, especially those without the resource to perform the weight updates or those applications in which sufficient tuning datasets actually cannot be gathered. Further, context lengths are expanding rapidly, partially due to model growth, largely due to transformer architecture variations, and is making this method of customizing models even more powerful. Now, while unfine-tuned models are capable of domain-specific behavior, it has been discovered that guided fine-tuning can improve their performance drastically. Due to the unstructured nature of the pre-training objective, unfine-tuned models show inconsistent and erratic behaviors. The fine-tuning process of recent LLMs does not serve to add information to the network, but rather to guide the model to develop inclinations to behave in a more consistent and desired manner. For example, for the domain of human interaction, models are better performers when fine-tuned for human preferences. Researchers have organized the creation of large human-annotated preference datasets to directly fine-tune pre-trained models using supervised learning to create some of the top-performing models today. However, the supervised approach is limited because creating such annotated datasets of significant size is very effort-intensive, slow, and costly. To mitigate this bottleneck, researchers from OpenAI released a technique which applies reinforcement learning to LLMs. In this technique, named reinforcement learning from human feedback, the environment is represented by a secondary model that has been trained on a smaller dataset of human annotated preferences. The LLM then attempts to optimize its outputs to the preferences represented by the secondary model. Not only does this mitigate the bottleneck of limited human feedback data, but the imperfect approximation of human preferences by the secondary model has actually been shown to be ideal for tuning the model without overfitting. RLHF has been shown to be especially effective and was key to the construction of the LLM which put generative AI in the public spotlight, ChatGPT. So, speaking of effectiveness, how do we even measure performance for generalist AIs? In the field of LLMs, evaluation is becoming more and more challenging for multiple reasons. The first and foremost challenge is knowing what exactly the model should be evaluated on. As models are becoming increasingly general, creating tests which comprehensively evaluate all areas which the model will perform on becomes difficult, if not fully impossible. Tests are becoming increasingly general and open-ended. Researchers are even beginning to evaluate these models on tests originally designed for humans, such as the SAT and the bar. Further, many tasks the model may be applied to do not have consistent or natural optimal behaviors. For example, given an identical prompt and response, different humans may perceive the model's response completely differently. Even further, many philosophical questions can be asked as to what trade-offs the model should make between individual preferences and biases. Aside from design challenges, on an implementation level, researchers are commonly experiencing test set leaks, in which information from the test set is found to be present in the data the model was trained on. This is difficult to avoid as datasets grow and duplication detection becomes increasingly challenging. What we've covered so far is a high-level overview of the common components producing the most impressive LLMs to date. I'll end this video by briefly discussing a few areas that have shown promise and will likely be included, or perhaps already are, in the next generation of LLMs. First, external information retrieval. If you compare human intelligence with current LLMs, while humans do store plenty of facts somewhere in their neural architecture, LLMs certainly seem to devote a much higher proportion of their neural complexity towards retaining facts. If a system could incorporate some form of external information retrieval into its design, it could potentially offload much of this complexity, making rooms for other types or levels of intelligence to develop within its weights. Further, explainability could greatly benefit from external information retrieval if citations were provided. This would also reduce the negative impact of hallucinations by making the model's outputs more verifiable. Second is external tool utilization. Models have shown increased performance when allowed to think out loud, meaning break their outputs into sequential blocks or something like it, each supplying information to the next. Researchers suggest that this is effective because, unlike humans, LLMs do not naturally acknowledge uncertainty, meaning if the model is uncertain, it does not behave any differently than if it was highly confident. This idea of working through ideas to increase confidence is strongly linked with what we know as logic. Also connected to this idea is the concept of adaptive computation time. LLMs currently apply the same amount of computation to every prediction. It's thought that if a model is more or less certain about a prediction, it could vary the amount of computation that goes into its predictions. Third is expansion of content length. As mentioned earlier, the design, structure, and content of a model's prompt heavily impacts its response and allows for instant customization. Many use cases can benefit from or even become feasible given especially large content lengths. For example, code recommendations on the file level are good, but project-specific recommendations receiving the entire repository as input could be even better. Common open-source LLMs have a context length around 2,000. The current GPT-4 model has a context length of 32,000, and for reference, the Great Gatsby is 72,000 tokens. Much of the increase in context length thus far has been due to a combination of growth in model size, as well as modifications to the transformer architecture. Themes of these modifications include recurrence mechanisms, relative positional embeddings, and integrating sparsity into attention. Lastly, I want to mention multimodality. Notably, GPT-4 is able to receive both text and images as input. While not much is publicly known about the technical details in this area, it is hypothesized that having a multimodal representation of the world could greatly deepen a model's understanding of it. If language is viewed as a top-down abstraction of the world, then sensation data such as imagery, sound, and others could allow the model to achieve a more fundamental bottom-up understanding of the world. Further, developing and linking concepts across different sources of input could allow a model to cross-verify its own beliefs. That's it for this overview of large language models. I hope you got something out of it, and if you did, please leave a like. If you want to see more about large language models and other AI topics, I will be making more videos, so consider subscribing. And any feedback is appreciated. Thanks.